Okay, so welcome everybody. This is another lecture on the logic to computer science. And can you hear me? Would you say yes? Okay, good. So we're gonna continue our discussions on some subfragment of propositional logics and how we can design polynomial time satisfiability solvers for these special kind of fragments. So last time we covered so-called Horn formulas, and we said because Horn formula have some special structure, in particular, if a Horn formula is satisfiable, then there always exists a minimal satisfying assignment. And using this, exploiting this structure, we can come up with a polynomial time satisfiability solver. So this is in a sense, stark in contrast with what's really happening for the general propositional logic formula, where the checking satisfiability is considered a very hard problem. It's a so-called NP-complete problem. If somebody can come up with a polynomial time algorithm, they can get $1 million. It's a solution for P is equal to NP question. So anyhow, so this is generally hard, but we looked at Horn formula and we found that for Horn formula, we can come up with polynomial time satisfiability solver. And then we were in the middle of discussing what really happens with another class of formulas called 2CNF. So if I give a reminder for what 2CNF is, 2CNF formula is a conjunctive normal form formula where each conjunct, each clause have at most 2 literals. So we looked at, so for this kind of a special formula, 2CNF formula, we can represent such a formula as a graph. And in particular, we can use the so-called implication graph. So the implication graph, given a 2CNF formula F, just activate pen. Okay, so 2CNF formula F, given a 2CNF formula, we can construct a graph G, which have a vertex set V and edge set E. And then essentially what this graph tries to do is it tries to capture all the implications expressed in the given formula F. So the vertices of this graph V, the graph G, are the either propositional variable appearing in the given formula F or their negations. And then there is an edge between these 2 vertices. Let's call it L and M. So these, vertices are literals. So we have a edge between literals if the formula F contains an implication that goes from L to M. So then implication will be encoded as these disjunctions of the negation of left-hand side of the implication and then the conclusion of the implication. And their disjunction is, this is a way to encode implication using disjunction. If such an implication exists in the formula F, so then we draw an edge from L to M. And we said, if there is an edge from L to M, then this graph should have an edge from complement of M to complement of L. That's because, because of what we already know. So this one is called contrapositive. So one thing we learned from really old days is that if P imply Q is, Q, and then negation of Q implies negation of P say the same thing. That's what we learned before. And in fact, if the P imply Q is included in the formula F, so this is one of the literals, clause of F. So if that is the case, then the same clause can also lead to another edge from negation of Q to negation of P. That is because in this Q is the same as negation of Q. So I mean, from here we can see that the same clause can lead to this implication. So that this graph has this type of duality property. If there is an edge from L to M, there is an edge from negation M to negation of L. So this graph is called implication graph. It's constructed whenever we are given 2CNF formula F. Okay. And then we said, so I show you some examples. And then one thing we did was we said, if I introduce a notion of a consistency of an implication graph, which means that intuitively what it means is there is obvious contradiction. There is no obvious contradiction from this graph G. So graph G encodes implication. Obvious contradiction in the implication is if we can show negation of P implies P in some sense, this graph entails there is an implication that goes from negation of P goes to P. Also, there is an implication that goes from P to negation of P. I mean, this can't be true. I mean, if this means that P and its negations are equivalent, which will never be the case. So this is an obvious contradiction expressible or detectable from an implication graph. So this consistency of an implication graph say there is no obvious contradiction like this. More graph theoretically, it just means that there is no cycle that has an edge that contains a vertex that goes from, I mean, there's no cycle that contains two vertices P and negation of P for some proposition of variable P, which means there's no, it's never the case that there is a path from P to negation of P, negation P to P. I mean, this kind of thing will never happen in this graph. So that's what this consistency condition means. And the key theorem that we talked about was actually, if the formula is a 2CNF formula, then satisfiability of the formula and the consistency of its implication graph is identical. They say exactly the same thing. And because of the consistency is a graph theoretic property, and this type of graph theoretic property can be checked in polynomial time in the size of the graph. So this theorem implies that we can check satisfiability of the formula F in polynomial time. Given a 2CNF formula F, we construct its implication graph by looking at this formula F. And then we check this consistency, which means we check the absence of cycle which contains P and negation of P for some proposition of value. So that can be checked in polynomial time. And in doing so, we can check the satisfiability of the original formula. So that's what how we can use this theorem to come up with a polynomial time algorithm that checks the satisfiability of a 2CNF formula. Now the question becomes why this theorem is true. Okay. So we said one direction of the theorem, we said is quite easy. So that direction is if it's satisfiable, then it is consistent. So this implication turned out to be quite easy. That's because the contrapositive of this implication, in Korean, 대우 of this implication, say that if implication graph is inconsistent, then the formula is not satisfiable, unsatisfiable. So that's what the contrapositive of this formula say. And that's actually very easy to see. The inconsistency of the implication graph really means there is this implication graph, this given formula F implies that there is just some proposition of variable P where we have a negation of P is equivalent to P, which can't really happen. So that's why the whole formula F should be not satisfiable. So the proof really expresses that type of idea. So another way to say this is, the reason why satisfiability became easy for 2CNF is because checking unsatisfiability is in general very difficult. But if it's a 2CNF, we can check only some specific kind of specific kind of unsatisfiability proof, and that is good enough. So this is a kind of this consistent implication graph tells us the only kind of inconsistency or unsatisfiability proof we need to go for is to try to find this P and negation of P where we have this type of cycle. I guess my explanation is perhaps confusing. So, but I guess what or most of you should now understand is what this theorem is saying. Okay, so this direction is easy, but the difficult direction is the other direction. So this direction is difficult. So that's what we're gonna look at next. So the other direction, which is say that if implication graph is consistent, then the formula F is satisfiable. It's not an easy direction. And to show that direction, actually what we did was we designed an algorithm. I showed you an algorithm. So this algorithm take up to CNF formula F, whose implication graph is consistent. Okay, so that's a situation where the right-hand side of if and only if that you see in the previous slide holds. And then the output, what we want to do with such a formula F and its implication graph is to come up with a satisfying assignment for this formula F. So this is an algorithm that tries to find such a satisfying assignment. So then the way it works is it's take implication graph and then it look at implication graph and then it maintains some partial assignment. So if we have an implication graph of F, which looks like this, implication of P, maybe Q, implication of Q and R. And maybe we have an implication like this, and then Q2 here and R2 here. Suppose we have an implication graph like this. So then initially none of the propositional variable has assigned some value. So initially we maintain the empty assignment. So the initial assignment A is gonna be empty map. It doesn't map anything. But then when we have some unassigned propositional variable, propositional variable whose truth value we didn't really determine yet. So then we pick any of such propositional variable. So let's say we want to pick P here. So once you pick P, because our implication graph is consistent, either we don't have a path that goes from P to negation of P. So this doesn't exist. Or there is no path that goes from negation P to P. So one of them doesn't exist. I mean, both of them, maybe that none of them exist. That's also possible. But it will never be the case that we have a path that goes from P to negation of P. And then we also have a path that goes from negation of P to P. Okay, so that's because of our consistency assumption of the implication graph. Well, let's assume that we have the former case. So we don't have a path that goes from P to negation of P. I think that's what's the case here. If that is the case, so then we choose, no. So in that case, we extend our assignment by saying the P should be mapped to 1. So we should we say that L should be mapped to 1. So now the new A is going to become, in our examples, it's going to map P to 1. Okay, and then it goes to the inner loop. And then in the inner loops, so now we assign P to 1, change the color. So P gets a value 1. That means negation of P will now get a value 0. So then when we go to the inner loop, and then in the inner loop, it say that whenever we have an edge that goes from M to N in this implication graph, where M has a value 1 according to our assignments. So which means when we can, I mean, if it's a, so m has a value 1, but n doesn't really get any value yet. So then we're gonna assign the value 1 to this node n, and we assign 0 to its complement. So in this case, now we have a proposition, this node p, I mean this literal p that has a value 1. It goes to an edge that goes to negation of q, but this negation of q doesn't have any value, so we're gonna assign value 1. But if you assign negation value 1 to negation of q, that means q will receive the value 0 here. Okay. And then we keep repeating this process as long as we can find an edge that goes from some vertex which is assigned to value 1, some vertex which is not assigned to value, I mean, which is not assigned any value at all. Okay. In this case, I mean, after one iteration, we are done. So then we go to the top level again, and we look at we see whether all the variables have a value. So at this stage, now our A will have a value P has a value 1, and then Q will have a value 0. Now we go to the top of these entire loops. In the top of the entire loop, we look at whether there's some variable which is not assigned. That's the case in our examples. This R doesn't have any value at all. And then we do the same thing. We check whether there is an edge in the path that goes from R to negation R, or the other way around. Then we found that there is no path from either direction. So none of them exist. So then in that case, we can make any decision. We can pick any of the literal, either R or negation of R, and assign the truth value. So let's pick negation of R here. So let's pick negation of R, assign truth value 1. That means R will receive value 0. So negation of R will got value 1, R got value 0. Now in this new graph, we check both the inner loops. In the inner loop, try to check whether there is any edge that goes from the one assigned node to a node which doesn't get any value yet at all. So then we can't really find anything. So then we get out of this inner loops, and then for outer loop, I mean, now our A has P1, Q0, and R0. And then we can't find, I mean, all the variables received a value, so that's it. So we get out of this and return A as the as the satisfying assignment. It turns out if you run this algorithm, then it's mostly based on some the marked value of nodes in the or vertices in this graph, and then there's some property of the edges. And then if you run this program, and then if you return A, then it's guaranteed that A is always a satisfying assignment. It's a satisfying assignment of F. And so that is what we want to see. Next. So this is always a satisfying assignment, and then that's because you can prove this by, well, first of all, this is a polynomial time algorithm. I mean, it always terminates. That's because whenever it gets into the loops, at least, I mean, this inner loop will get executed at most n times, because whenever you execute this inner loops, some unassigned variable receive a value, and there are at most n variable in our program. So this inner loop will be run at most n times. Outer loop will also be run at most n times. So any command in this program will run at most n times, and each command takes at most order of n times. So this entire algorithm will run order of n square. I mean, not order of n square, but n times the size of the formula. Okay. So now we want to argue, so it terminates, but we want to see that it's always find the correct, I mean, it is correct, which means it always returns satisfying assignment, assuming our implication graph of the given T2CNF formula F is consistent. Okay, so figuring this out actually is not that obvious, but you can do it by using the idea of invariant, which I talked about last time when we discussed the algorithm for horn plots. So here's some. So here are loop invariants. So here's the loop invariant. So let me show you the program here. Okay, so the program that you see on the right-hand side of the slide. So then there are, okay, maybe it's better to move. Okay, so this program, its correctness, which means it always returns satisfying assignment, can be proved by these two invariant. Outer loop has this outer loop invariant, inner loop has this inner loop invariant. So here's an exercise I want you to do, which is to show these two are indeed invariants. And then furthermore, if the outer invariant implies what's returned is a satisfying assignment of the formula F. So before actually, if you already understood everything, you can go ahead and then solve this exercise. If you have no idea, let me just give you some intuitions about what really happens. So these two invariants really tells us some story about what's really happening when we run this algorithm. So when we have you can view it, but although there is a formula F, this is really a graph theoretic algorithm. So you have a bunch of vertices in the graph. And then there are edges between them. Maybe like this. And so on. So there's edges between them. And then what this algorithm say is, while this program is running, each of the nodes will be marked in, will be one of the three cases. It's either marked with 1, or it's maybe marked with 0, or might be unmarked. Because, this is like this one unmarked. So it's one of the three cases. Either it has a value 1, I call it that kind of node or vertex is called true node. A value 0, that kind of node or vertex is called false node. And there's another, yet the third kind of node, which didn't really receive any value at all. Okay. And then this outer loop invariant to say that whenever, if you just focus on all the nodes marked with 1, okay, then there will be some node which can be reached from 1. So if this somewhat like a schematic view from node 1, there are a bunch of things which you can reach. And then the outer invariant to say everything which is reachable from 1 will have a value 1. So that's what this outer loop invariant to say. So this means that the graph that I showed you here doesn't really satisfy the outer loop invariant. But what this outer loop invariant try to tell us is, the entire loop try to do is to really try to do this kind of a marking. Whenever there is a node which is marked with 1, it tries to make sure that everything which is reachable from 1 will have a value, will be marked with 1. Now, for the inner loops, talk about something which is satisfied by this type of graph where everything reachable from 1 is marked 1. So this means like if something is, you may have something like some node which is marked with a 0. They can reach some node marked with 1. That's not a problem at all. So this is some closure property with respect to the node marked with 1. Okay. Or there's a property with respect to true. Now, for the inner loop, think about some kind of intermediate stage before actually we reach, this type of nice marking. Okay, so think of the situation that's really coming from here is a really very good one. So let's say this is a very good kind of configuration that we want to achieve. But suppose we are in the middle of achieving this good configuration, which means that maybe in some case, there are some nodes from 1, but some nodes which are marked with 1, some nodes which are unmarked. Okay, so if we are in a situation like this, then we can kind of achieve the situation on the top by marking everything which is, by changing the value of this unmarked node to 1, right? From unmarked to 1, so that we can go from this intermediate situation to the situation that we want to achieve on the top. But if we are in a situation where we have a 1, and there are a bunch of nodes marked with 1, and a bunch of nodes unmarked, but there are also a bunch of nodes, some which is marked with 0, then we will never be able to transform this guy to the one on the top, because this part is already marked with 0, right? So what this inner loop invariant say is that we are all, in some sense, what does it tell us is that we are always in this type of situation. Everything which is reachable from 0 is either marked with 1 or unmarked. Okay, so there is at least some hope that we can convert this to the good configuration where everything reachable from 1 is marked with 1. So what that tells us is the outer loops really try to maintain this type of property. It does something to maintain this property and make some progress about this property. So initially, if there's some unmarked node, and then each iteration of the loops will pick one of the good unmarked node and marked with 1, and then want to convert this one into this kind of good configuration. So that's how this outer loop is working. And then the inner loop start with some kind of incomplete configuration like the one that I showed here. So maybe so some part is marked, some part is unmarked, and then it gradually transforms this configuration into the one that you see on the top. Okay, so that's how the algorithm works. Okay, I feel that my explanation may or may not really help you to understand what's happening. But anyhow, so that's my explanation. Try to prove this theorem. So I will give you maybe 10 minutes to solve this problem. Yeah, first, try to show that if the y outer loop invariance and then negation of the loop condition that you see here. So there's a loop condition here. If you take a negation of the loop condition, because when you got out of the loop, this loop condition is false, still outer loop invariant is going to be true. And try to see why the outer loop invariant together with negation of the loop condition implies what we have, this A is gonna be a satisfying assignment of the formula F. So that's the property we want to guarantee. And invariance and negation of loop condition implies that property. And so first try to see why that is the case, and then try to show that this invariant is really an inductive invariant. Inner loop invariant is also really inductive loop invariant. Yeah, okay. So I will explain what in the answers for these questions. So, and also regarding the question that Jian raised, I think although you see only number 1 in the slides, this literal L can be not P. So setting A of not P is equal to 1 really means setting A of P is equal to 0. Okay? So the key fact is this literal L in the slide can be negation of some propositional logic for propositional variable. Assigning 1 to the negated propositional variable means assigning 0 to the propositional variable. Okay, right. So, I mean, if you have any other questions, I mean, just ask me in the chat box. You can write in English, or if you feel more comfortable, you can write in Korean, no problem at all. Okay, so let's see how this works. Let's first see that why the outer loop invariance and then the negation of the loop condition implies what we want. And that is because both of them, so this, this loop get executed when there is some unassigned variable. So the fact that when we get out of this loop means every propositional variable in formula F now have a value either 0 or 1. Okay, so this implies the negation of this entire thing implies that in a sense A is complete in some sense. It assigns the value for every propositional variable appearing in F. So A at least is some kind of the assignment that we are looking for. We don't want partial assignment. We want, in a sense, full assignment. And so FA is some full assignment. Now the question becomes, does A actually satisfy F? So the next question is, A is going to satisfy F. That's the question. And then the loop invariant tells us that is the case. The loop invariant say, if we convert F as an implication graph, so F is converted as an implication graph, some of the node in the implication graph will be marked to 1. Some of the nodes will be marked to 0. So let's mark nodes like this. So some of the node will be marked to 0. Okay, marked true and marked false. And then because A is complete or A is full, every node is marked either 0 or 1. And then the outer loop invariant to say there is no way to reach 0 marked node or false marked node from 1 marked node. In particular, that implies there is no edge from 1 to 0. So this kind of thing will never happen. Okay, what does that mean? That means because each edge encodes an implication, right? So all the implication that appears in the formula F will always go from 0 to 0, or 0 to 1, or 1 to 1, but it will never go from 1 to 0. Okay, so now if you remember the truth table of the implication between two formula P and Q, this implication is false only when this P is equal to 1 and then Q is equal to 0, right? So this implication graph say that every implication appears in F are gonna be true because the false case, which is the hypothesis is equal to true, conclusion equal to 0 will never happen. I mean, there's never going to be an edge from going from 1 to 0. Okay, so these two facts, we get out of the loops implies we have a full assignment, and then the loop invariant of the outer loop invariant, which is everything which is reachable from 1 or get value 1. That implies that none of the implications appearing in F, or none of the clause appearing in F is going to mean that none of them is false. Okay, all of them are true under A. So in other words, A satisfies F. So that shows outer loop invariance, and then the negation of the loop condition implies we have a assignment that we are looking for. And now we have to show that this outer loop invariant and inner loop invariant are maintained. So we first look at the we look at the execution of the body. So then if the outer loop invariant is true, but not all variables are assigned, then there must be exist some propositional variable. So let's call it P, which didn't really receive any value at all. And then because the graph is consistent, either we don't have an edge from what we don't have an edge, the path that goes from P to negation of P. I mean, this doesn't exist in the graph, or we don't have a path that goes from negation P to P. I mean, not one of them doesn't exist, or both of them. I mean, that's also possible. So then in that case, we pick only one. So our algorithm pick one of, I mean, if that's the case on the top, it assigns value 1 to P. And then negation 1 to 0. Okay, so initially before executing this, we have a graph where some node is marked with 1, some nodes are marked with 0, some unmarked. So there are a bunch of nodes which are unmarked. But by doing this, we increase the nodes which is marked with 1. So we increase one node marked with 1. We also increase the node marked with 0. Okay. So yeah, these are the 3 nodes. And then this one is marked with 1, and this one is marked with 0. So we have to make sure, okay. So that's what we do in the first step of the algorithm. So that's this is step of the algorithm. Then we go into the inner loop. We erase. Okay. So we go to the inner loops, and then because we hit the inner loop, we have to check whether this invariant is true. Inner loop invariant is true, and that is the case. That's because so we can prove this. Okay, let's check whether that's indeed the case. So if I mean, for every node that's already marked with 1, I mean, we don't have any problem because everything reachable from 1 is marked already with 1. So the condition of the loop invariant with respect to this part. So the inner loop invariant say that there is, I mean, everything reachable from node marked, the true node marked with 1 is either marked with 1 or unmarked. So it will never be the case this reachable node from true node is marked with false. Okay, so everything reachable from true is either true or unmarked. So for everything, but everything reachable from 1, they are, because of the outer loop invariant, they are always gonna be marked with 1. So this one will not cause any problem with the inner loop invariant. The only potential problem is this guy. Okay, this one is marked with 1, which we newly added to this marking scheme, and they may cause a problem for the inner loop invariant. But now, because of the consistency, the problem doesn't happen. So for instance, suppose this doesn't really satisfy this inner loop invariant. That means there is a path that goes from 1 to 0 somewhere, like this. Okay, so this first case that goes, I mean, there is a path that goes from 1 to 0. I mean, in the middle, we may go through some node which is unmarked. That's no problem at all. So it just say in the implication graph, if we can reach node 0 from 1, if this case happens, then there is some contradiction. And what's the contradiction? The contradiction is when we choose this node, I mean, the node here, we chose the nodes that satisfy, I mean, this condition. There is no path from that node to its negation. So this type of path cannot exist by our choice of this node. Okay, so by this choice, this will not happen. There's a contradiction with that choice. Now, for this second possibility, which is that this node 1 can reach to some node marked with 0, cannot happen either. That's because if this happens, so then, I mean, every edge in this path, we can think about it's contrapositive. So if we said, if there is an edge that goes from R to S in this graph, there is always an edge that goes from negation of S to negation of R. So if there is a path that goes from 1 to 0, and then suppose it reach some node marked with, say, R, mean, okay? So then there is also a path that, so this is, say, P, and there's also a path that goes from negation of R to negation of P. Because of this property, I mean, if we have a one implication, we can always have it's contrapositive. So if there is a path that goes from P to R, then there should be a path that goes from negation of R to negation of P. Because R is marked with 0, negation of R should be marked with 1. And then because of the invariant, the outer loop invariant say everything which is reachable from the 1 marked node should be all 1 marked. So this one should have been marked with 1 because of the outer loop invariant. But that also contradicts our choice of P. Our choice said we pick L, which is unmarked. So that's another contradiction. So that none of these two cases will happen. Okay. So, so when we reach okay, P0, let's use a box here. And this is assigned 1, and now P box is assigned 0. And so what we argued was when we run the first two statements and reach the inner loops, then the inner loop invariant is true. And then we can actually show that this inner loop maintains the loop invariant. It's not, I mean, I'm not going to do this, but I mean, it's a good exercise to check whether you fully follow you understand this algorithm. So inner loops maintain this loop invariant, which said there are no paths from the true node to the false node. Okay. It's possible that we can reach some unmarked node from the one marked node, but we will never reach the 0 marked node from 1 marked node while running this inner loop. So that you can show this body of the inner loop maintain this invariant. But now when we get out of these inner loops, then this inner loops we will finish this inner loop when there is no edge that goes from 1 marked node to the unmarked node. So while inner loop is running, we may be in a situation, so we have a 1, 0, and there are unmarked. And then while inner loop is running, we can have a edge that goes from 1 to unmarked, although we will never have an edge that goes from 1 to 0. So this one doesn't exist, but the one on the top may exist. But then when we finish, this type of edge doesn't exist either. Okay. Because I mean that's the termination condition of the loops. So when this inner loop terminates, that means everything which is marked with 1. And if you follow the edges in the graph, you will always go to a node that's also marked with 1. So all the edges are inside of this 1 marked node. Okay, so that's what we're gonna get here. So that is exactly the outer loop, the properties of the outer loop invariant. So everything which is from true node is also true. So when we get out of this loop, outer loop invariant is maintained. So this is a bit not very easy. I mean, if I say pose put this question as a say final exam and ask you to come up with a good outer loop invariant, inner loop invariant, and show that they are indeed invariant, and also try to show the correctness of the algorithm using these invariants. That's not going to be very difficult, but given these invariants, the checking this invariant is actually an invariant and they implies what we want, it's substantially just, I understand this is not still easy either, but it's substantially easy. So I encourage you to, when you kind of have time, encourage you to think about, to go through this reasoning process for yourself. In particular, try to show that this maintenance of the inner loop invariant. This is also not super difficult, but it requires some of the thinking. Okay. Okay, let's move on to the next. Right. So then what I want to do next is, yeah, we said 2CNF formula have a polynomial time solve. So then you might ask, okay, if we increase 2 to 3, maybe still we might have some nice, some good polynomial time algorithm to check the satisfiability for 3CNF formula, which means there's a 3CNF means that it's a conjunctive normal form formula where each clause has at most 3 literals. Okay, 2CNF means the 2CNF here was conjunctive normal form formula where each clause has at most 2 literals. 3CNF means conjunctive normal form formula which have at most 3 literals. Now you might think, okay, maybe 3CNF is also very easy. It turns out that's not the case. So 3CNF it's as difficult as the satisfiability problem for entire propositional logic formula. So the key concept that key kind of observation behind this difficulty, or equal difficulty of 3CNF satisfiability and the general satisfiability is that the key concept is this so-called equisatisfiability. Equisatisfiability between two formulas says the following. It says that if the formula F is equisatisfiable with formula G, if this condition is true, if F is satisfiable, if and only if G is satisfiable. It doesn't say F and G are equivalent. Okay, F and G might say something completely different, but as far as the satisfiability is concerned, they are the same thing. Then at this point, you might ask, okay, if I know the F is satisfiable, then this if and only if condition doesn't say very much, because I know that F is satisfiable. So any satisfiable formula G is gonna be equisatisfiable with F. Okay, but this notion of equisatisfiability makes a lot of sense when it really helps us to design a new algorithm. That is because we can, even when we don't know F is satisfiable or not, we can find G, which is equisatisfiable with F. Okay, so if you know F is satisfiable, then finding equisatisfiable formula is very easy. But even when I don't know F is satisfiable or not, sometimes it's quite easy to design an algorithm that convert F to some other formula G, which is not necessarily equivalent, but it is equisatisfiable. And then what we can do next is that we can apply this satisfiability algorithm, this checker, on G instead of F because G has a kind of more regularity properties. So then this theorem say, actually for general propositional logic formula, there is a polynomial time algorithm that converts this F to 3CNF formula G in such a way that F and G are equisatisfiable. I think the best way to see this algorithm is actually see some concrete examples. So here's an example, the formula F. Then, I asked you to solve this, but let me just answer this question for you. So, this is a general propositional logic formula. It's not even CNF conjunctive normal form formula, but we can convert this to the conjunctive normal form formula. as follows. I mean, ET satisfiable conjunctive normal form formula as follows. So we decompose this formula into all of its subformulas. So the one subformula is F itself. Maybe which pattern? So one formula is F itself. The other formula, subformula is removing the negation. We have P and Q or not negation. R or negation of P. And then the other subformula is P and Q. The other subformula is R or not P. And then we also have a P, Q, R, and negation of P. Okay, so these are all the subformulas that appears in this formula F. Okay. So what we do is that we introduce, in addition to PQR, we're gonna introduce many more propositional logic formula, and we're gonna claim that we're gonna fix its meaning by saying that these propositional logic formula, each of them will mean the subform will be equivalent to the subformula. For instance, we're gonna introduce, say, P1, 1, 2, 3, P3. So maybe writing the that is better. So we will introduce P3. That should mean exactly the same thing of negation of a P. And we will introduce P4. That will mean exactly the same thing as R or negation of P. We're gonna introduce P5. That will mean exactly the same thing as this guy. And then P6. And then P7 for the thing. So then now once we introduce these multiple propositional variables, so then we can encode what each of these propositional variable should mean just using a conjunction of essentially using 3CNF. Okay, so let me show you how we do it. We first have to say P3 is equivalent to negation of P. So that means P3 is equivalent to negation of P. But this one is the same as is equivalent to not of P3 or not of P and P3 or P. So this thing encodes in this implication side of the implication. This encodes this side of the implication. Okay. And then you can notice that the formula that I wrote is actually a 3CNF formula. And then we can do the same thing for P4. So we said P4 is equivalent to R or negation of P. And that is, if I encode this implication using negation and disjunction, it's the same as not of P4 or R not of P. And for the other side, that's the same as not of P4 or not of R and P. And this one can be written as, because of the distributivity, so P4 or not of R and P4 or P. So we can write it like this and so on. And we can do the same thing for P6. So P6. Sorry, I was not quite right. What am I doing here? So no. So I should have written it a bit different way. Yeah, so this really, instead of writing like a P, what we have to do is we have to write it as a P4, terms of R, or instead of negation of a P, we use a P3. Okay, so any of the subformula except propositional variable, we're gonna re-express them in terms of propositional variable that we just introduced. Okay, we introduced P3 for negation of P, so we just write it P3 here. So then the rest is the same as what I did before. We can express this by implication in terms of 3CNF. We do the same thing for P6. So P6 is a complicated formula, but I mean, this side of the P6, we know that that's going to be equal to P5. And this side of the P6 is going to be equal to P4. Yeah, I don't do P5, but just let me do it for P6. This part is the same as P5. This part is the same as P4. So what we have to encode is P5 or P4. And that can also, by just using the usual rules, you can rewrite this as a 3CNF. I mean, all of these can be expressed in terms of 3CNF because the propositional variable that appears in this encoding is just like you see here and here. Always, we only deal with the 3 propositional variables. So we can express these things in terms of 3CNF formula on the right-hand side. Okay? By first expressing this by implication as a conjunction of 2 implications, and then rewriting this implication using negation and disjunction and so on. Then you can express this as a 3CNF formula. And then finally, P7 is going to be, we should have another encoded, we should have some formula which the P7 is equivalent to negation of P6, which is again can be expressed as the 3CNF formula. So once you do it, then we can encode this formula F by taking the conjunction of everything. So conjunction of this guy, this guy, this guy, and this guy, and also one more, and 2 more. One is for P5. The final step is, all of these, what they are really saying is define the semantics or meaning of P3, meaning of P4, meaning of P5, meaning of P6 and P7. So it didn't really say we are interested in the satisfiability of formula F. So finally we have to put a formula P7 there. So the entire, but because each of these components can be expressed as a 3CNF, the conjunction of all of these will become a 3CNF formula. So that's an example, and let me show you the proof. The proof is exactly what I said. So it lists all the subformula of F. In this case, we even list the propositional variables as, regard propositional variables as subformulas. And then we put all the propositional variable appearing in this formula F in the beginning of this enumeration. So it says P1 is the first propositional variable, Pm is the mth propositional variable that appears in the formula F. And then the others are the other subformulas. And then we introduce a new variable Pm plus 1 up to Pn. And essentially we encode, we define the 3CNF formula Gi, which say Pi should have a meaning Fi. Because we have this Pm plus 1 up to Pn, which encode the meaning of all the subformulas here. Meaning of all the subformulas here. So all these subformula, we have a corresponding subformula here. I mean, this encoding of this by implication can be written as a 3CNF. So if we take a conjunction of 3CNF Gn plus 1 up to Gn, and then finally if we add the last propositional variable Gm, that gives, in a sense, that encodes the meaning of the original formula F. Okay, so these are, as I said before, each of this Gi, in a sense, fix the semantics of this Pm plus 1 up to Pn. So they are defining the meaning of all these new propositional variables that we introduced. The final Pn say, by the way, we are interested in the satisfiability of the entire formula F. Okay? So now if you do this, this formula G is equisatisfiable with formula F. They are not equivalent because, for instance, formula G has more propositional variables, Pn plus 1 to Pn. They are extra propositional variables. So they are not equivalent, but they are closely related. In particular, formula F is satisfiable precisely when the formula G is satisfiable. If formula F is satisfiable, pick the value of satisfying assignments and then look at the value of P1 up to Pm in the satisfying assignment. Evaluate all these formula Pm plus, all these subformula Pm plus 1 to Pn, and then use that evaluated value as the satisfying assignment for G. So you can construct satisfying assignment for G from satisfying assignment for F, and also vice versa. So this gives this polynomial, this describes the polynomial time algorithm. Okay, so we have about 4 minutes. Then so I'll tell you a little bit about Xor formula today, and then maybe continue talk about Xor formula and then this workset algorithm on next Monday. So this Xor clause is Xor is an exclusive OR. If this Xor of a P1 or P2, P1 Xor P3 means only one of them is true. Okay, so this in some sense corresponds to our usual kind of the natural meaning of OR in the natural language. And this XCNF is very much like a conjunctive normal form, except that instead of having disjunction of literals, we have a XOR of literals. Okay, so you see that the first conjunct or first clause is a XOR of P1 and P1 XOR P3. The second negation of P1 XOR P2. The last one is P1 XOR P2 and negation of P3. Okay. And it turns out this although the usual CNF is the satisfiability is not an easy problem, for XOR CNF, XCNF, the satisfiability can be done in polynomial time. Okay, that's a bit surprising. You just replace OR by exclusive OR, but all of a sudden the satisfiability becomes really simple or much easier. Okay, so maybe that's perhaps a good place to finish today's lecture. So I want you to think about this, and then I will give you an answer in the next lecture and give you a bit of intuitions about what happens here. So if you are familiar with, maybe you might or might not heard about this something called the Z2 in mathematics. So this is just a set of integers which contains only 0 and 1. But when you write the Z2, we are really thinking about plus operations, which is defined in terms of modular 2. So if you have a for plus operation on this space is defined by if I have x plus y, we do usual, let's write underbar, usual x plus y, and then we take a mode 2. And then actually this Z2 have also multiplications and so on. So behave very much like the usual set of integers, except that everything is taken with modular 2. And it turns out this XOR is nothing but the plus operation in Z2. So many of the nice devices that people developed for solving the equations involving integers or maybe natural number integers or numbers can be applied to the XCNF formula. So that's how we can derive a polynomial time algorithm. So it's a very close relationship with what's really happening in the numbers. And then for numbers, if you have a constraint, there are many ways of solving constraint. We can use one of these algorithms to solve, design a polynomial time algorithm. So that's what we're gonna talk about next Monday. Okay, so that's it for today. As usual, I will stay about 5 more minutes. So if you have any questions, you can stay and ask me.